Okay, thank you very much. I really appreciate the invitation. It's a pleasure to come and talk to you guys. Say about some of the things that we're doing. For the past 15 years, one of the problems that my group has been looking at is formulation of coarse-graining descriptions of flows in fluid solid systems. These are important for being able to do large-scale reactor simulations. So the flows are fairly complex. I'll try to give you some illustrations of what the flows are like. Then we can see how we go about building those models. So the structure of the talk is if you talk about the views of fluidization operations. I'm assuming that not everybody in this room is a chemical engineer, so I will spend the first few slides kind of walking through to build up the background for you, instead of assuming that you know. I'll talk about the flow structures, I'll talk about examples of stabilities, and then I'll say a few words about the models. So this portion might be a bit mathematical, so this is for the specialists. And then I'll talk about qualitatively what coarse-graining does to give you a flavor for it, and then talk a little bit about some of the things that we do in this classic problems. So why call something a fluidized? You have a collection of particles and you're sending gas through the system. And this is a movie that was that I got from a friend of mine, he's on roads. And so this is put there for two reasons. One, to bring a smile on your face. The other one is to show that what really happens. Here, this bed was originally packed with putting a rubber back at the bottom, and you put some sand on top of that. And the sand behaved like a solid. And so it was able to keep the rubber duck under heat, even though it had a lower density than the sand. And once you start putting some air through, the sand suspension began to behave like a liquid whose density is higher than that of the rubber duck. And so the rubber duck was able to write the sand and begin to behave like a fluid. That's what we mean by a fluidization. Because the sand particles plus the air mixture, because you are levitating in the upward flow of gas, it begins to behave like an fluid. And if you tilt that bed when it's happening, you'll find that the surface of the bed will continue to remain horizontal, which is again a fingerprint of the liquid horizontal. The picture that you saw where you saw some bubbles erupting at the top is what we call a gently bubbling bed. If you look at what kind of particles people use in industry, the classic paper by Geldart, he classified the particles into four groups. He called them group C, A, B, B. C's are very cohesive particles, and then you have some particles in between, and these particles are very difficult. So if you take a cohesive particle and try to fluidize them, then it's very hard to fluidize. They won't expand. You keep looking at it. After a while, the bed will break up into pieces. Oops, not doing it. Then it's going to give you an apple. It's not going to fluidize properly. We should create. Okay, now we should create. See. So you're not really forming a apple, and the bed cannot be fluidized properly. So you can't levitate those particles. So you have to come up with some other means of breaking up that agglomerate. So very rarely do we need to work with those types of particles. If you go to very large particles, they also don't fluidize very well, and people tend to operate them with spouted. So you have a conical shaped bottom, pretty high velocity gas, and you try to use circulation. This is a typical operating mode. But most of the industrial systems operate between these two regimes, where you have typically 75 to 150 or 200 micron particles, density of between 1 and 2 grams per cc, which is that not material. And the reason why people choose this size range goes back to lots of reasons, like fluidization bulk and also separating particles from multiple reasons. So if you look at particles of that type, I'm trying to imagine what happens. if you take a collection of particles and you put them on a grid, then the particles will stay at a fixed bed. If you start putting gas to that, it stays at the fixed bed. So the pressure drop per unit length increases as you increase gas flow rate. You reach a point when you start supporting the weight of the bed with the pressure drop you apply, the bed begins to fluidize, inhomogeneities form, inhomogeneities get worse as you increase, and then you start getting something that looks like a turbulent bed, where you have gas-rich pockets that are pretty erratic, and you have liquid-rich, solid-rich pockets of emulsion that are also erratic. But here you have a case where the solid pockets are continuous, the gas-rich pockets are discontinuous. You go higher, they do phase inversion, you get gas-rich pockets become continuous. The solid-rich pockets become discontinuous. They tend to get inhomogeneously distributed over the pipe cross-section. This would be something representative of a well-defined bubble. This would be more like something here, clusters and streamers. So these white strips are the streamers of particles. So if you look at most industrial reactors, they tend to operate either here or there. So either you have a turbulent bed, or turbulent is a generic word, not in the sense of a three-phase spectrum, and then you get a fast fluidization. So which one of these beds that you choose, and then for your process, it depends upon a number of reasons, number of considerations as to what happens, how well you get back mixing in the fluid. Sometimes back mixing is desirable, sometimes you don't want to have them. Other cases, will the particles break up? So if you look at the industry, you will see a lot of technologies operating in this regime, a lot operating in this regime. And the same technology from one company might be in this regime and another one might be in that. So you get all these different operations. So one of the basic questions is that you see homogeneous flow patterns. So what is about how do they scale from small scale to large scale? Often do pilot experiments, you get this kind of flow. And if you think of single-phase turbulent flow, we often talk about how you change the vessel size, then the scale of turbulence also gets out. So the size-dependent scale comes in, and we need to understand how well can we anticipate what kind of flow structure changes are going to happen as we go from small scale to large scale. What kind of tools that we need. So these are the kind of driving questions, and that leads to what kind of models are needed at different scales, how you capture them, and people work on different fields. What you need to worry about different scales is that if you look at if you look at that part, I'm showing you here. Here is a movie that was taken by people at NETL, Frank Schaefer, and this movie is taken where you have a vertical pipe through which you are trying to flow gas and particles up. That circulating fluid where our fast fluid is the regime that flow apart. So keep in mind that the net flow of gas and particles are going up. And these are, we can see that near the wall, they're actually falling down. So it means that they're going up in the center and they're falling down in the wall. There's a big degree of internal refluxing of the solid that are going on. And if you see the flow patterns, they are very inhomogeneous. You can see structures that are propagating. And if you look at that, the same thing, taking a high-speed video, will show that if you look at that, you can see the particles. You can see that here is that you can see clusters and streamers that are going near the wall region. And if you look at even closer up, you can see the particles are very diluted in some region, they are very dense, they are falling down. And if you look more closely, you can actually see particles that are colliding with each other and bouncing off. So the particles are really moving around the inside, they're hitting each other, they're moving around. These were taken with somewhat larger particles for visualization purposes. This is then people are very expecting finer particles that are more typical of what we do. So you start seeing these kinds of flow structures. If you look at the flow structure, some of these finer scale flow structures are nothing of the order of 20, 30, 40 particle diameter. And if you're working with 100 micron particle, if you're talking about 40 particle diameter structure, I'm looking at something of the order of a few millimeters. And the vessels are often of the order of meter. So the chance that I can resolve these kinds of flow structure in any large-scale flow problems becomes a challenge. Question is that if you don't resolve, so what? Will I make a mistake in the predictions of the flow problem? How do these kinds of flow structures affect the performance of the reactors and so on? These are the questions. So for large-scale reactors, they're often of the size of several meters in diameter and then several meters tall. Any practical industrial scale simulation often uses grids that are 10 centimeters, 20 centimeters, something like that. So you are not going to see any of the structures that are smaller than that. So how do you coarse-grain to account for the consequence of those structures, and how do you first understand where they come from, and so on? These are the kinds of questions that we worry about. So if you look at this kind of flow problem, you find that particles do collide with each other, and then they execute the mean flow, they will also execute the random flow. And this has led to a theory called kinetic theory of random materials, where particles are treated essentially as large molecules, and the kinetic theory of gases have been adapted to describe the flow problem. And that's a fairly mature field where people have worked on for over 25 years. So we have come a long way in saying that those types of descriptors do a decent job of capturing the small scale, the effects of small scale dynamics of this particle. And so these random motions give the particle an effective particle-based pressure and an effective particle viscosity, so we can begin to think of them from a continuum perspective with the average over long material. And these structures of the order of 10 to 50 particle diameters, they pick up particles, they shed particles, and these are realistically what's happening in these flow problems. And from a chemical reaction point of view, if you think about that, if you form a cluster, and if all the gaseous reactants are here, the particles here in the cluster may not see a reaction. And therefore, the effective utilization of the particle is going to be a lot smaller in that case. So you can expect that your transfer rate, your utilization of the catalyst, your reactor performance are very affected. So it's not just the hydrodynamics that you have to modify and understand that. You also have to think about how effectively you are transferring reactants from there to the particles, how they are reacting. So everything from mass transfer, heat transfer, reaction, all will have to be corrected to represent the consequence of the structure that we are never going to be able to solve in a large scale flow problem. So today I'm going to talk only about hydrodynamics, but then we consider all these transfer phenomena as a whole when we do these applications. So typically you find that there are a lot more of these kind of clusters in the wall than the core. That's why you see there's so many particles in the wall, they all fall down, there's nothing to support them compared to the center. In city phase turbulence, we talk about how the fluctuation energy is different from near the wall and the core region. But here, in addition to that, all the particle concentrations are also picking up the lateral variation, which then sets up secondary flows, and we need to understand how the flows happen. So if people think about what are the kinds of big picture questions that drives this fluid particle flow research in the last 20 years, we can talk about questions at the small scale. These are what causes those bubble-like voids that I showed you before, and the cluster that I showed you before, and what are the minimum physics that we need to put in to try to be able to capture those flow problems. And people do the direct numerical simulation, people do particle resolve simulation, particle dynamic simulation, try to address and learn about these kinds of questions. And when it comes to the device scale, which is what I'm going to talk about today, is that we have structures at different scales I showed you in the movie, and we are often interested in the large scale flow structures. How these small scale flow structures work together to give you large scale flow complexities, and then how that will affect the reactor performance that we can do in predictive analysis. And so how do you efficiently simulate them without having to resolve the right stuff? So those of you who are already simulated turbulence can see it's not very different from the same question that we ask conceptually. But when it has solids that are being handled, often solids from one vessel go to another vessel, you do something else to them, and you recycle them back, and so there's a circulation loop, and you can get instabilities associated with these kind of coupling between them. But I'm not going to talk about this today. The slides I skipped, we're supposed to talk about what those are supposed to do. So we do some work on that as well. So my main goal is going to be to talk about device scale challenges. How do you think about coarse problems when you deal? The idea of coarse-graining cuts across many disciplines. Multi-scale is a buzzword that you see in every discipline. And this is, in a sense, we have multi-scale flow problem, and how do you think about coarse-graining in in this kind of aerodynamic flow problem, which is one example. So a couple of slides of the equation. If you're not in the field, you don't have to worry about understanding the words what they are. The main theme of looking at the large scale flow problem is this. You have all these particles that are colliding with each other, and they are transferring stresses through each other. So we can begin to pretend that we can treat that as a continuum phase. So we treat the particle phase as a continuum, and then we treat the gas phase as a continuum, so you have an interpenetrating continuum. So you have two phases that are flowing together, they're competing for volume, because one can't occupy the volume occupied by the other. So you have to share the volume between them. So you have two species, so you have to have two mass balances, flow of mass, flow of gas, and flow of solid. And you have to have momentum balances. Navier-Stokes equation to say that I have to conserve the momentum of the gas in some appropriate fashion according to Newton's second law. Similarly for the collective particle. So you have two momentum balances, one for the particle and one for the gas. So basically the governing equations are just that. And if you start from a point equation, which is something we can write as the Navier-Stokes equation for the gas and the Newton's equation for the particle, and you go through averaging procedures, you can derive this effective continuum model. People have done 50 years ago, and there's a lot of loose ends that people have been trying to tighten as years go by, and so, but we have come a long way. So this is not a new thing in this equation. So if you look at that, all you need to know is that I have your mass balance for solids and a mass balance for gas. And we are only looking at in this example, just kind of a boring flow with no reaction. So there is no reaction, just a simply aerodynamic flow problem. So there is no change in mass of particle by reaction or change in mass of gas by reaction. And if you look at the momentum balance, we have a pair of momentum balance that I told you before. On the left-hand side of this equation, we have the usual inertial terms. So it's exactly like the inertial terms that we have for the Navier-Stokes equation. On the right-hand side, we have all the forces that are acting on the system. And every term, as we know in the Navier-Stokes equation, is per unit volume of the system. So I told you the inertial terms are there, one for the solid, one for the gas. And on the right-hand side, you have the gravitational force acting on the gas or the particle, rubbing surface. And because they're sharing the same space and they're going together, they're talking to each other, and so they're exerting an equal and opposite force on each other. And that's what we call the interface interaction force. And then if you have a gas phase, then you have the pressure in the gas phase, you can talk about viscous stress, so there is an effective stress in the gas phase. And then this is what we call the effective buoyancy force, or immediate buoyancy force generated in this problem, goes into the gas phase. And this comes in because you saw that the particles are colliding with each other and they were transferring stresses with each other. So you got various mechanisms by which particles transport momentum. So that's basically the framework for all of the models. So if you look at this volume phi here represents the volume occupied by the particles, and phi g the volume occupied by the gas, and they have to add up a lot because they're sharing the same space. And they use and can magnify the velocities of the two phases. And these are the local average quantities, just like we take the average of molecules in the region, give you continuum density and continuum velocity for the phase. It's exactly the same split. So if you look at this, in this equation, we have continuum variables, but there are no terms that you don't know. These are all, there is no unknown terms that require constitutive models to be done. And if you look at these momentum equation, on the left-hand side, there are no terms for which you need constitutive models. So if you look at constitutive models, I need three terms. What is that? What is the stress in the gas phase and what is stress in the particle phase? So all the details of what happens at the particle scale have been lumped into these three terms for which we need to develop constitutive models. And what you put in there dictates the behavior of the flow. And if you look at many of these flow problems, in this problem, the larger particles, the principal contribution coming from the gas is the pressure. So even though you have a deviant load express that giving us the effective viscosity, that doesn't do what really do for this problem. So we can actually neglect that and replace that with just pressure. You don't need to do anything. And then if you look at the interface interaction force, that is principally a drag force that the gas exerts on the particle. People often talk about what about added mass, what about Safman lift force, what about the history force that comes in, and so on. They're all not important. Only thing that matters is the drag. And if the drag force, the thing that we need to simply know is that it depends upon the relative velocity between the gas and the particles, and some multiplicative constant called the drag coefficient, and that depends upon the Reynolds number at the particle scale, they were defined here, and then it depends upon how many particles there are. This is the textbook thing people developed 50 years ago, and they have been refined, but the basic framework is already there for all. So we know this stuff. So the drag coefficient is simply a function. So I told you we have a handle on this term, we have a reasonable handle on this term. And if you look at the third term that we have here, if you look at that term, I told you that the particles have a free flow and a random flow, and that is where the adaptation of the kinetic area of gases have been used to develop constitutive relation. I showed you this movie before. So there are, so using that, I will simply say that I'll simply say that there are models that people have developed for describing the stress model, the stress term that we have. So we have a fairly decent constitutive model for all of these terms. So I told you that we have a continuum model framework, and we have terms for all of them. Then the question about the top, right? That we have everything, so we should be able to solve. But the thing that we did back in the late 90s is to see what happened if you analyze those equations and see if you can predict them. What we showed is that indeed, that if you want to get a nice homogeneously fluidized state like here, all you need is drag and gravity, you'll get it. Everybody knows that the textbook item, the field. And we also showed that the reason why you get instability like this is because you have a competition between inertia and the inertia, then the drag, the coefficient, tends to destabilize the problem. And if I have to give a very simple, intuitive way of thinking about it, the gas wants to go up, the particles don't want to go up, the gravity wants to come down. So the particles move aside and give an opening for the gas, the particles can go down and the gas can go up, they can go their one way. So segregation of the flow allows a decreasing of the overall pressure drop that the system has got to feel, and that is the natural tendency for the system to want to not to be homogeneously distributed. Just like we saw in the cohesive bed, you got a rat that's an extreme form of segregation, but you get this tendency of the bed to segregate so that the particles can go down, the gas can go up. That's what's driving the instability. What is fighting the instability? It is the collision that was taking place between the particle, and the particles want to congregate in one region and then leave another region, devoid of particles, then these particles are colliding, and then random motion diffuses the particle away, so that you start getting a more homogeneous distribution. So this mechanism by which this is occurring is very robust. We did bifurcation analysis. We showed that whatever model you put in, as long as we have physically reasonable model, you're going to predict all of these flow structures. So all the flow structures that I showed you in the movie are very easy to capture in your model. That means that the model has got enough meat in it with relatively simple constitutive models to capture the kinds of flow structures those movies are revealing. This is one case where the models came first, the predictions came first, and then the experimental movie verified it came later. So if you now try to say, okay, now we have the model, it has all the right features, so why don't I just simulate the whole thing? This is where the problem comes. So we use an open source platform that has developed over the years. And I'll show you some simulation. Here, we are doing some simulation in a fairly large region. And to keep the wall effects away, we do periodic domain simulation, which is about 64 centimeter by 64 centimeter. Put lots of grids, and then we apply a pressure drop. So we start with a homogeneous suspension of particles and see what these equations predict. And you find that after a while, the equation says that they will become inhomogeneous. And this is your volume fraction scale. So a red means one particle, blue means not so many particles. You start getting inhomogeneous flow structure. These are time dependent, and what you are seeing is a snapshot of the time. But if you put more grid, they get a different structure. If you put even more grid, I get a different structure. If you put more grid, you get even different structure. So you start getting more and more fine structure as you put more and more grid. And the reason why we are getting down here, now we are talking about grids of the order of few millimeters. While here the grids are 1 centimeter, you find that the grids, you are indeed, the equation says there are these fine structures. And indeed, as I showed you in the experiment, these fine structures are of the order of 20 quarter diameter, 30 quarter diameter. So these are real fine scale structure that are seen experimentally in models are predicting because they are there. The reason why they happen, this kind of fine structure that happen, is because the stabilizing force that comes from the collision between the particles are extremely weak. So the destabilizing is very strong, the restabilizing is very weak, so you end up getting fine structure. So that we understand. So stabilizing is, that's why you get a small things. So this is the scale, this is already a very large scale supercomputer problem. So how are we ever going to do a real reactor which is many meters in diameters and height, if I can't put that even in a 2D, let alone going to a 3D. That's a challenge. So when you do them in 3D, again you have the same kind of problem of grid resolution. As you put more and more grid, you start getting finer structure. So with all this background, what I am trying to tell you is that this is your real reactor. Whatever I do in a transient flow simulation, I'm going to put a finite size grid. If I can blow it up, I'm going to see fine structure underneath because these fine structures are very fine in structure. I'm not going to see it. If I blow it up, I'll see some particles. Even further some small region there. So most of the equations have been developed for flows at that scale, and when you simulate those equations, you see structures at this scale. But what I really want is structures analyzed in a large reactor. So this creates a problem because I cannot put enough grids to 500 by 500 grids here and then deal with the large reactor. So what happens then is that you have this structure. So the engineering needs are that they need structure to probe the macroscale flow features. So that we can somehow have to figure out a way of averaging over the consequence of those fine structures. That's people do in simulation. And so it's like taking that these two fluid molecules that it showed you that has all the meat in it to capture all the flow structures. Somehow we have to coarse-grain those equations to try to come up with effective model equations. And that's where the crux of the work has been. And so to do that, what we do is we do detailed simulation because the kind of information that you need to build these filter models are not easily obtained experimentally. Even if I can manage to look with fine scale, I can only see where the particles are, I can see where the fluid is. I can't get what the force on the particle, what the fluid force. So the many things that we need for building these models are not something that I know how to go to the lab and measure. And therefore, we decided to take the computation approach. We got lots of processors started doing large-scale simulations of model flow problems with very high-resolution simulations so that we can generate computational data that we can analyze to look at what kind of coarse-grained models we can use. So the question, we began by doing two-dimensional simulation. We also do 3D. But those of you who work in turbulence will say, hey, 2D turbulence is different than 3D turbulence. So how can you even do 2D? And it is a natural question to think about. If you look at single-phase turbulence, you really need the 3D aspect. So 2D doesn't make sense. You won't get all the features because you only have dissipation but not a source of the small scale structure. But it turns out that for the fluid solid phase, it's okay. You can get everything in 2D. And we have and 3D, I'll show you that 2D and 3D give you similar results. The reason for that is the source of the structures. In single-phase turbulence, we often talk about how eddies form in the large scale and work their way down to cascading to small scale. You have some backscattering, but that's second order effect. The principal effect is the energy going from large scale to small scale force structures. But in this class of problem, that's not what is driving the instability. What is driving the instability is that on a small scale, the gas and particles don't want to be together. If they move, the particles move away, it makes it easy for the gas. So you first form these small scale flow structures, and then they coalesce to give you larger scale flow structures. And that small scale flow structure segregation is even there in 1D, let alone going to 3D. Because 1D means you get the structures that are that prevent bypassing, so we don't do 1D, so we do 2D, and it allows gas to bypass the regions of which gas. So we did a lot of simulations in 2D, then we do some in 3D to show that whatever you got in 2D is indeed physically acceptable, we get similar results, and therefore we can apply those things in 3D. But 3D simulations are extremely expensive for us to do. At least 10 years ago when we were doing it, they were very expensive. So we do these detailed simulations, we generate computational data, and then we store lots of snapshots. So that becomes our resource. And then we post-process them in many different ways to try to extract as much information about the fine structure. So we take the data, we filter them at different length scale, and then we look at all the quantities that we need to develop a filtered model. When you look at filtered model, these are the original models I showed you. The filtered model basically, this is the actual volume fraction, this is the filtered quantity and the fluctuation. Exactly like the way we think of in RGD or Reynolds averaging kind of approach. So we do all that, and then we try to process what are these fluctuating quantities that come into the equation. We have filtered velocity, fluctuating velocity, filtered velocity for gas, fluctuating velocity, and so on. So we do all these quantities, we analyze them. I don't want to bore you with all of these details, but if I skip all these things, just like in Reynolds averaging, we find out that you get the mesoscale stress contribution that comes in due to the sub-filter scale fluctuations that are happening in the system. And you get a correction to the drag. It turns out in single phase flow, we spend all the time worrying about these effective viscosity due to the turbulence. Right? That's what we worry about. How the turbulent viscosity is much bigger than laminar viscosity. That's what we worry about in single phase flow. So you get that, but in the two-phase flow that we're talking about, that is almost an important question. What matters is that how do you find the communication between the gas and the particles get modified because you have all these fine structures there. So correcting for an effective drag becomes the principal worry in all of these kinds of problems. So you don't need all this content, skip all this detail. And so I'll just show this just to give you an idea of how much correction there is. So what I'm showing you here, this is in 2D and 3D, just to show you that you get similar results. What we are talking about are how this effective drag coefficient, when you multiply this with the velocity difference, that you get the interface interaction force, and then how it varies with the particle volume fraction. The first thing you notice is the blue curve. Blue curve is what the drag laws they told you about that you can open up the textbook and see. It says that when you increase the volume fraction, it is becoming harder and harder for the gas to go through. That is called the hindered settling or hindered drag. And this is what you would get if in my filtered region everything was homogeneous. There was no subfields. But if you realize the actual flow, or if you say, you know what, underneath that there are inhomogeneities. So if I now tell the gas to go through, it's not going to go through uniformly. It's going to find its way through all these regions that are lower in gas, in particle concentration, and then meander their way through and not feel the presence of the gas. We find out that the effective communication between the gas and the particle is a lot smaller. And that's what this curve says. If I filter with different filter sizes, what I should be using is going down significantly. So when I go from some dimensional filter size by factor of 8 in this case, I find that my effective drag coefficient is 50% off. And to give you an idea of how big this filter size is, for the typical particle that people use in this case is only 1 centimeter. So what it says is that in this flow problem, even if you look in the 1 centimeter region, there are so much fine structure underneath that. If you don't recognize that you're going to be wrong in talking about the force that the gas exerts on the particle by 50%. So if you go to even larger grids, so if I'm doing an industrial scale reactor with these grids are this big, then when it goes through, all the structures that I am not taking into account are going to push the curve even further down. As a result, you will be completely off. And the simplest example we can do is at one point people said CFD is useless for two-phase flow. It can never be done. And that was the simplest argument that people gave is that if you take a single particle and then if you drop it, it accelerates and reaches the one as the single particle terminal settling velocity. I think one doesn't have to go any further. So the experimentals will come and give this kind of a right. Okay, so instead of gas particles falling down, if I move the gas up at the single particle terminal velocity, you will be able to hold the particle at the one position, because all that matters for sedimentation is the relative velocity between the gas and the particle. But now instead of one particle, you put lots of particles, because of hindered settling, you will blow the particles out of the bed if you have the gas going at single particle terminal velocity. So any time you put the gas velocity approaching single particle terminal velocity in a bed, it will blow the heck out of the blow out the particle out of the bed. That's what all the CFDs were predicting. But all the industrial reactors are operating at 3 times the terminal velocity, and they're perfectly fine. So you have no hope of ever doing that. And the reason why there's no hope is that they're all pretty large grid, and they are grossly overestimating the interaction. And if you recognize that, you know what, you are grossly overestimating the interaction, but you're not putting finite grid to resolve this structure, and that's why you're getting nonsensical results, which is earning a bad name for the CFD. So all these results are trying to fix those problems by correcting these directions. So since then we have gone through several generations of that, and the way that how the field has evolved is that a corrected quantity is expressed as 1 minus H3D, and H3D is a correction. So when the number is 0, it means that there are no corrections. The microscopic drag law that you can work with the literature is fine. When the number is getting larger and larger, you're making bigger and bigger corrections. All that what I want you to see is that numbers can get as high as 0.8, which means that real systems can have only 20% of the drag by the time you go to the big bang. That's why you are able to operate at 3 times the terminal velocity and still not blow the particles out. That's simple. So we can provide an explanation as to why these industrial reactors are operating without being blown out of the ventilators. So to do this, we are indeed doing 3D simulation as told you before. So we see some model problems like this, model problems of different concentrations, and then we filter those results. So a lot of post-processing to generate this kind of data. So this data requires many hours of supercomputing time and many hours of post-processing to try to generate these. So we have done all of those results. In reality, it's much more complicated. So it's much more complicated. I will show you one thing in this to just illustrate how results that are seemingly non-intuitive comes out when you do this kind of analysis. I showed you that this effective drag coefficient is 1 minus the function h. That is a product of how big your filter size is, and then something that depends upon the volume factor. So the previous slide, I showed you that quantity is only a function of volume factor. That was our first generation model that we generated. And then now that when you look at the data more closely, there is that's not very true. There's a second marker that you need to think about. And then the thing is, if you now look at one volume fraction and one filter size and look at the second slip velocity marker, you find this h goes up at a given volume fraction and given filter size as we increase slip velocity. So h goes up means the drag is very low. So if I come and tell you that I have one particle and then a gas going past the particle, as the gas velocity increases, the Reynolds number goes up. Will that increase the drag coefficient or not? You will say, of course, it's going to increase the drag coefficient. Because drag coefficient goes up and the Reynolds number goes up. The drag force goes up and the Reynolds number goes up. But here I say the drag force goes down and the Reynolds number goes up. It's the exact opposite of what you will see when you do a single particle conclusion. And the reason why it happens is because this one lumps many things into it. It lumps the tendency of the particles to segregate and the drag force it produces all into one. So when you have a higher relative motion between the gas and the particle, the gas pushes the particle more vigorously away, creating a bigger path, and that in turn creates less communication between the gas and the particle. The gas goes faster. That's why. So it is because the gas flow rate relative to the particle influences the microstructure in a way that higher the slip velocity, higher the segregation, and therefore the lower drag. Let me explain what was initially non-intuitive once you start doing these kinds of calculations. So we are doing these and trying to explain these and quantify these. So I will. So we do them in 3D, and you don't need to worry about pressure. So I'll just show you one example. to know any of these is any good. All is filtered model. So we do two things. One of them is that we have to verify this model as one element. So we take this constitutive model, put them into our two fluid equations, coarse-graining two fluid equations, put coarse-graining and simulate them. We get a certain set of result. Then we take some small scale test problems, put large lots and lots of grids so we can resolve all of these problems and get what is the analog of your direct numerical simulation. So we say that the coarse model should give the same coarse result that you obtain from a fine scale simulation. So we do that first to make sure that our coarse model is faithful to the fine scale data on which the coarse model was built. Having done that, then it's okay, now we have to compare against experiments. Ultimately, we have to compare against experiments. And large scale experiments are very time consuming. So national labs have generated these data sets and then they have made repositories available for people. And one of them is done by the National Energy Technology Lab in conjunction with the consortium of PSRI. And they have several test problems that are posted. And one of them is a bubbling problem. And this is filtered down to 7 meters tall and 1 meter back, 5.9 meter diameter. This is a pilot plan, not a real plan. This is a pilot plan. And then they have put this different kind of distributor, and then they do this data, and then they ask people to challenge, and you did that too, right? Because many people in universities are trying to see if the models they are developing are going to be able to capture the kind of data that they have reported in the system. So we take our models and then we do these simulations to see whether we have made any progress or we're still in step one in our research. So just to give you an idea, the data they give is really simple. So as we go from the bottom of the bed to the top of the bed, the pressure is decreasing linearly when the bed is operating in a time average. This basically means that when told the particle concentration is essentially uniform. The bed goes to about 4.5 meters tall. After that, we have a free-board region where the particle is segregated. This is so simple that we can write an empirical relationship for this almost trivially, and that's how the field was back in the 1970s and 60s. But it doesn't tell you how to scale things up. If you put something else inside an internal, how it will change, it doesn't tell you. And through CFD, we are trying to see if we can capture it. So if you take those models that I wrote saying that we know exactly what this fine scale data results are, and if I try to simulate them with finer and finer grids, by the time I put 200,000 grids, that's a large number for two-phase flow because the number of variables is much larger than we have in single-phase flow. And you find that these simulations are already taking a very long time. And the thing is, you find that it takes a while for it to develop, but eventually you blow the particles out of there. You are not going to be able to keep it. So it means that even 200,000 is not enough. You need to go to much finer number of grids if you want to be able to solve the problem without doing any coarse-graining. That's what we mean to say, without doing any coarse-graining. But when we do coarse-graining, whether you use 40,000 or 70,000, we are able to capture what is going on with reasonably well because we have corrected for the fact that we have fine-scale structure to represent. And indeed, if you look at the flow in this coarse-grain, we can begin to see the kind of fluidization flow. Has it solved all the problems? No. But there are certain features of the experiments that we are still not able to capture properly. And so we are working on trying to figure out how to capture these systems. So the gross features we are beginning to capture well. And this is principally because we figured out that in the coarse grids, your drag is highly falsified and how to correct for that, how to identify the scaling for that is what we have done. So to kind of summarize what I just said, the overarching question that I've been is saying that we would like to use CFD in conjunction with heat transfer, mass transfer reaction to look at large-scale flow problems. But we only want to look at them with the macro scales and we don't want to resolve every fine structure. Construct here macro scale framework without having to resolve the fine structure. It is very similar to what we could do in our simulation structure framework. And the approach that we have done is that we first understood the origin where they come from, where they come from the instabilities. And then we tried to figure out how to formulate the filtered model, and then we computationally generated data sets to try to develop this filtered model. It's not very different from frequent single-phase flow doing direct numerical simulations with small domains and using the statistics of that to better develop the quantitative simulation. So idea-wise, they're exactly the same as how people have been doing in experiments, except that the term, which really matters, doesn't exist in the phase flow. It is specific to two-phase flow problem. And where we have done is we have finished analyzing aerodynamics, we have gotten time average results, and we have done mass transfer, we have done some test reaction problems as well, but there are really not open domain data available for reactor problems to do, so we are not doing that. So nothing to present and verify the open domain at this point, but we are showing the methodologies. So this is what I just said. But if you look at where the field is going, just a few quantifications for a few minutes and then I'll stop. If you look at everything that we have done it for the single size of particles. But in the real fluidized system, we have a distribution of particles. And we have other complexities that comes in. We have complexities of the form that the particles can have some cohesive force to attraction. You can have sometimes liquid bridge forms between a few particles causing a agglomeration. You can have particles rubbing against some surfaces and picking up charges, or particles picking up charge, so you get electrostatic interaction between particles. In polymerization reactors, that is the biggest concern that they have. So you have these non-idealities that come into play. So how do you deal with all these non-idealities? The kind of two-fluid model framework that I talked about becomes very cumbersome for those applications. So the field is drifting towards either the Lagrange simulation phase, where you solve the fluid phase still in a continuum fashion, but the particles are done in a discrete fashion by using some approximation methods. It can be parcels, it can be the direct numerical simulation or the collision tracking. So there are many different scales of this. So that's where the field is evolving. So the question that my group is currently looking at is how should we think about those kinds of problems? So we are looking at coarse-graining for Euler-Lagrange problem. So we do simulations with billions of particles in domains like this, and then we are averaging to see how should I think about coarse-graining that one. The same spirit as what we did for the computation models, we are applying to these problems. And if the kinds of flow structure that you see here, they are the kind of flow structures that we saw in the movie. So you do create those kinds of flow structures. And here in the case where you pick up a wet particle, here the dry particle is the wet particle. And so when you put wet particles, I think the movie will play. Yeah, they play. So here, for example, when you do wet particles, the behavior is different. So what is the role of wetness in the system? How should I coarse-grain? How should I think about capillary? Because these, if you look at the size of the domain which we are simulating, they are a joke. They are only a centimeter by centimeter or something like that. And ultimately, I am applying them to real large-scale reactors. So we are learning something about the source and the effects of fine-scale structures. So we can still work our way toward large-scale structures. And then, so as I told you, the thing that we are looking on the effect of all of these, and for that, we really need to work on either the Lagrange type of approach to first understand what happened with the small scale and then see how we will respond. So that's the kind of summary that I have, I believe. That's my last slide. And I will show that, this is almost a 20-year exercise, everything from bifurcation analysis of continuum problem that we were doing back in the late 90s to what we are doing now. I've had many collaborators, students who work on that, and I'm just presenting their work. I've had lots of support from ExxonMobil continuously for 20 years. It's been a blessing. They value the work, they say, do whatever you want, and give me the money from Aspergerity, and then similarly in Synchro, and the Department of Energy to do these things. With that, I'll stop on that section. Got it moderately unit from one at the University of Manchester, along with Yeah, problem is that all it gives you is the volume factor. Yes, sir. A single thing of the sensors, single layer. And at that time, at least, they were using simply linear magnification. And you could see a bubble like that. And if you go put my finger inside that, I'll get negative volume factor. So other than recognizing that you have a density variation, you couldn't do that. And for building this kind of model, knowing that there is a segregation of particles alone is not enough. I really need to look at how fast these particles are moving so that I can try to infer what the force is feeling. So the NEPL movie, the Max Schaefer that I showed you about, was designed and built with that in mind. Even though they are only the wall region, they put some probes to see and say as well, is that now you can actually see and track the motion of the particles with image processing. And from there, once you know the particle velocity, you know the particle acceleration, so you can know what the force is going to be experiencing and see if you can figure something. So this high-speed videos in relatively dilute system is possible. Now with tomography, now people are trying to put these two layers of tomography. And then LS Fan has got this what he calls these volume tomography. All of that are still 2-4 scale. Resolution you can get is still 1 year of the order of 7 centimeters. So this is not enough to see what it is. So that's why I considered all of that and I said, no, to go to the lab of water purity.
Upon the first order, is it possible to estimate the scale of software distribution and the difference? How many pointers do you actually to the scales? How many pointers do you have to measure the scale? If there are unknowns, that would be able to give it any distribution. So it's possible to estimate the scale of the
So you're asking me if it is possible to estimate the length scale of the smallest structure we are seeing. We have thought about that from two perspectives. The first perspective is that let's imagine that we have a homogeneous structure. And then throw in a small scale disturbance and see what are the length scale that I can amplify, or the maximum growth rate length scale. So that's one thing. That is a homogeneous system. But that doesn't tell you what happens when the system becomes very homogeneous, right? Because that's only for seeing. So if you don't do that length scale, you don't capture that length scale, you're not going to see proper evolution of that. So we did that, and that length scale does come out to be of the order of 10 particles per diameter, 6 particles per diameter, based on current generation of the model. That's what most of the simulations that we do, we work our way down to 4 or 6 particles per diameter. The fine scale simulation. So what we do is we do simulation to a very fine scale and then show that our coarse filter properties no longer change when we make the grids fine. But when we have this highly inhomogeneous state, can we use that in energetic and see how small it was to? So we try to look at the energy spectrum to see how fast it decays from those simulations and see. We don't see in the usual log plot, we're hoping that we get a straight line so we can see that we don't see that. We get these very nice curvature, and by the time it goes toward the end, it becomes so noisy, we don't know how to do it. So we have looked for that and we have been unsuccessful. Maybe some turbulence people like you can come look at that and make more sense out of that. But we have not been able to see. So our rule has been that get down to about 4 to 10 particle diameter simulation. So most people who do these type of work either use 4 or 6 or 10 particle diameter resolution when they want to get really resolved results.
So we will do a paper that way about the average, the time average before the volume average. But that, basically what I mean is the time average with the turbulence inside, and then you see the volume average with that capacity, how the distribution is. And then the second question is how you get the constitutive relations close to the boundary.
Close to boundary.
Close to.
Well, the first question is that what about volume averaging or time averaging? Now, if you look in the single phase turbulence, people talk about completely trying to remove all the time dependence and Reynolds averaging all the way through, so you try to solve a steady state problem. Or you try to resolve the coarser scale flow structure in transient and model only the smaller scale flow structure in Lagrange simulation. When we began by hoping for the first line, so we can average all of them out and we can come up with essentially steady state coarse-graining model. I still would like to do that. But when we first did that, we made some assumptions which seemed to seemed promising at the time. But we didn't recognize that the real challenge is the drag. That we did not afford. We were thinking more like what happened in single-phase terminals. And we were trying to put the blame on stresses. And it seemed to work under some conditions, and it didn't work. But then we were clueless as to where to go. That's why we went this route and we realized it's all the time. And now that we have learned this, we want to go back and see if we can fix the other problem that we haven't done. The reason why it's important is that ultimately we are looking for predicting very simple time average properties. Why should I do transient simulation to predict time average properties? Can I not predict time average properties by using time average properties? Very valid question, but the field doesn't come to the point. That's the, I forget the second question.
The one
Oh, it's boundary. What? I told you that once we take a region and then say I'm going to filter everything in the region and give you an effective quantity. We first said that everything inside can be explained based on how many particles there are. That's where we started. And what we found out is that we did that. When we went to near the boundary, we had to come up with a correction. Because what happened is the boundary was not the same as what happened. So we tried to come up with boundary correction. But then later on we realized that maybe the problem was that our assumption that everything inside can be expressed in terms of volume factor. There is some other microstructural characteristics that we need to recognize. And if we do, maybe I don't need to worry about that because in the second microstructural characteristic is different in the water region, automatically captured. That's when we went to the second marker that we were taking. And when we went to the second marker, it appears that we don't need further volume. Well, we have the thing that we are talking about taking a microscopic track model and then seeing how we need to correct the fact that we are using coarser grids and then you are not resolving the time structure. So our argument hope has been that our model should not be dependent on specific microscopic track model. So we have tried to see what happens if we use different types of microscopic track models. The most common one people use is MNU, but there's another one very popular called least-stress drag or Dirac-stress drag. We haven't used Dirac-stress drag, but the least drag from Piper's group, they did a version of that that captures and includes that. So we can compare to that. We find that the same idea of
yes, if you want to follow,
we have done that. We have done some paper and we have shown that if we do that, we get the same kind of. All of the drag goes up. This is nothing to do with you put any of the drag law. Because this problem comes because there are fine structures. All the drag laws are homogeneous. So if you don't resolve fine structures, you're going to have a problem with all the drag laws. So the fractional correction that you need to any drag law is what we're doing. They're not saying there are different incarnations of drag law for the fluid now. When you use one of them, gas flow is one of them, then is beach dry is one of them. So if you look at them, they are slight differences, but they all have the same qualitative. So whichever one you use, of them will give you the same kind of application diagram, point structure, same kind of activity and scale. I mean, it is not because we are using that. Yes, sir.
You said that lag is the one significant one.
Well, if you look at the Allen mass force, this talks about when a particle is accelerating, it is taking a little bit of the fluid around it, it is accelerating the fluid too. If the density difference between the gas and the particle density is so different that the direction because of the gas is very little. If they are a liquid, that would have been a substantial. If the liquid solid system, that would have been a substantial contribution. For gas solid, the density difference is so much it doesn't make a difference. The same thing that happens for all the other, they call it passive pores or other pores. We always see that there is a raw gas that comes in. Raw gas is so much smaller than raw particles. It makes no difference. But the magnitude of the drag force is proportional to the weight of the particle, because after all you are levitating the particle. So the ratio between the density, that's not that's 1%, less than 1%.
So if you change the drag model, do you have to redo the scale?
No, the reason why, that's why I was saying, we are trying to do that in a way that's why we talk about we were talking about a fractional correction. That's why we talk about beta over beta micro, right?
Exactly.
But then if you change your beta micro, fractional correction is still the same. So we have tested that to say that if you decide that I don't like your drag model, I use this drag model, tell me how to correct, then my answer would be that the fractional correction is going to be very similar between different drag models. So we look at it. So we are not trying ourselves to any one. So we have tried a couple of different drag laws.
And we found that
remember, these are averages over many realizations. So it is an average of the bands. They all lie in the same band. So if one says, I have to correct a 1 and 2 drag law, you get only 20% of the drag. It's correct. Because of the point structure. Another model may say, well, it's 21%. I'm not going to worry about that. I'm trying to go between 0 and 0.2. I'm not going to worry about the point scale.
so the thing about coarse-graining is to reduce the complication. But in case, in my continuous degree, so this is you focusing more on the volume function of the dispersed space. But in case in my continuous space, there is a sharp velocity equation. Obviously, I need to go for a fine. I need to go for a fine and to capture the velocity.
If you have a fine velocity gradient, if your goal is that you want to simulate the fine velocity gradient, this is not the way you want to go. You have to solve it. On the other hand, if you say that there are lots of fine velocity gradients everywhere, so I somehow want to recognize that fine gradient, but on a coarser scale, I don't need to worry about the fine gradient. Then we can talk about it. The kind of objectives of the problem. Here, the objective is that people who do large-scale reactors, they want to worry about the large-scale coherent structure. If all the particles in the reactor are on one side of the reactor and all the gases going on the right side of the reactor, we want to know that because that means they are not contacting each other. So but they are not worried so much about these 8-particle cluster or 10-particle cluster. They are worried about if the gas and particles are seeing each other or not. That's what we worry. So when you want to look at the macro scale innovations, which causes the biggest problem in loss of productivity, then it makes sense to go in this fashion. But if you say, I want to understand exactly what happens in high velocity jet that's coming into a fluid bed, that I want to do a reading, this is not the way. You have to think of something. So this is not an answer to all class of problems, answer to one